Hello, welcome to my second YouTube video on the COVID-19 virus spread. In a previous video, we were looking at ideas behind flattening the curve. In this video, we'll look at the situation, what will happen when we do these restrictive measures in Canada. So if I can ask the camera person to take a look at my mathematics here. So COVID-19, let's say it lasts 21 days, and after 21 days, statistically, people recover from the disease and stop being contagious. That's one thing that we're going to take into account. A second one is the size of Canadian population is about 40 million, and the current restrictions that we have in our society. I have chosen the value 1 in 12 for the contagiousness, pretty restrictive. That would mean that one person in 12 days would infect or have tendency to infect one person as a result. So that's a very low, that's a severe social distancing aspects in effect. So over 12 days, one person would tend to infect one person simply just by getting too close or something like that. So a bit of mathematics, a bit of definition. We're going to divide the model into two pieces. First piece is for the time being from the beginning till the duration of the disease, 21 days, we're going to have one model coming in. And after 21 days expire, then we're going to have another formula for the model. So let's look at the first model that we have. Capital P of T is the current amount of people infected up to the time T. So all the people that had it up to the time T, the infection. So how is that changing? So the rate of infection of that quantity is proportional to the R value, it's the contagiousness, so 1 in 12 that we have taken. It's also proportional to the amount of people that have been infected. Now this is for the duration of 21 days, so everybody that has been infected up to this point is spreading it. So times capital P. But this term is not going to be that important, but it's going to come into limelight a little bit later. This is a mitigating factor because after a while, if so many people get infected, then they start infecting people that are already infected, so it doesn't really work. So this term is telling us somehow the probability that we're going to hit with the infection a non-infected person. After 21 days elapse, a model changes. Reason that it changes is that people who are getting infected 21 days ago are already departing from the pool of the contagiousness people. So the rate of infection now is proportional to the R value, still 1 in 12. But now the pool of people who are capable of infecting other people has been reduced. Those are the people that are currently with the disease that are not cured yet, so to speak. And so the difference between them is the P of T minus P at T minus the 21 days. So that's the group of people that are capable of infecting people. Past the 21 days, they are no longer infecting anyone. And then times, again, the probability that these infected people will hit a non-infected person. So this is a model that we have, and we're going to do a computer simulation. We're going to go on a computer in a little while and ask the camera person to move to the computer. Again, to summarize, this is the model that we have. We're going to do a kind of a computer simulation, how that's going to spread out. 21 days for the disease, 40 million in Canada, and the infection, the contagiousness value is 1 in 12. Pretty severe restrictions into movement and activity within the society. So I'm going to ask the camera person to kind of move with me carefully. Don't show any kind of stuff that is in the room. This is not the cleanest room. So here we have Octave Online. It's a MATLAB kind of an online user interface computer thing, so to speak. So we're going to look at this this chart. So this chart tells us over how long on this axis we're getting the number of days, and the height is telling us how many people are infected at any time measured in days. So 1 unit is 10,000. So the peak that we are reaching here is about 7 million. So, and it's about 180. So let's say 6 months after the infection. By the way, we started with 1,000 people infected at the beginning. Okay. That is not that crucial in the model, but it's kind of a little bit realistic. So 1,000 people are infected at the beginning, and so 6 months later, with this scenario, we're getting the peak, about 7 million people infected in Canada at any time. So this is not the rate of infection. No, no, no. This is actually the total amount of people infected at the time. Remember, the disease lasts 21 days, and we have this optimistic scenario that statistically everybody survives it. I know there's unfortunately a fatalities associated with this, which is very sad. However, statistical models, we can assume that they recover. So the K value there in the model is not being changed by the unfortunate fatalities. So the peak occurs, as I said, 6 months later. So I'm going to run the model now and just look at the rates of infection there. And here it is. Behold a graph which again gives us now the rate of infection as opposed to the total amount of people infected. So we see that the biggest rate of infection is about, let me kind of get close, about 5 months since the beginning. We get the highest rate of people being infected, and it's coming up to about 150,000 people per day being infected in this model. Then we hit the 6 months when we had the peak of the amount of people, but then the rate is becoming zero. People are kind of theoretically 0 people infected per day. And then 7 months later, we're getting actually people dropping in infection. That means that the new infections are smaller than the people leaving the pool due to being cured or recovered from the disease. And then it reverts slowly back to zero. So that's the model that we have. I'm going to summarize it again. We had a model where we assumed a fairly restrictive social distancing in Canada and shutting down non-essential businesses. One person would have tendency to infect one person in 12 days. And that's it. So again, the projections that are being discussed in society now and people talking about 6 months till peak and all that stuff, now we have been able to kind of support these things, kind of a make your own model of COVID-19 at home type approach. So this is something that a university student or anybody who is interested can do, and just kind of double check what you've seen in the media and just kind of do it at home approach. Thank you very much, and take care. Bye-bye.